Yes. Yeah. So let's take a look at some equations related to linear equations. So make sure that you know our slope-intercept equation of a line. The main thing to remember is that your slope is your coefficient on your x, and that our b is the point that we hit the y-axis. We call that our y-intercept. So it is always of the form 0b. Now the slope is considered a constant rate of change, hence why we end up with a line. We can write that as delta y over delta x. Remember that delta y over delta x can also be listed as y2 minus y1 over x2 minus x1. So just so we're aware of some of those formulas. Now, as we go through this investigation, if there are any other formulas, I think there's one I might give you related to lines that might be helpful, but those are the main ones that are very useful that you're going to see in linear equations, okay? So let's take a look at problem number 1. It says that you are riding a stationary bike, and after 2-minute warm-up, you begin pedaling at a constant rate of 4 minutes per mile for the next 5 miles. What quantities have values that are changing together in this context? So let's think about the things that are changing together. Like as we do this, these things change. Can anybody think of something that is changing along the way in this problem? Can anybody tell me an idea of something they think that is changing together in this particular problem? Yes. Yes, so let's put that as distance that we've pedaled. What else is changing along the way? What else is changing along the way? That distance that we pedaled is changing, but what else is changing? Can anybody think of anything else? Yes. So the miles, that would be the same thing. So if you wrote miles that we've pedaled or distance that we pedaled, but there's another thing that's changing. Yes. How long it takes, the time. So the main two things that are changing for this problem together, as the time changes, the distance changed. So those two quantities are changing together in that context, okay? So part B says, what does it mean going at a constant rate of 4 minutes per mile? What does it mean that we're going 4 minutes per mile? We don't usually say it quite like that, but we're going 4 minutes per mile. Yes. Yeah, so so if we think, usually we're thinking of a rate as a if we think of miles per hour, we usually kind of think of it in the opposite direction. We kind of flip it. So 4 minutes per mile, you can also think of that if we take the reciprocal of that, that we are going 1/4 of a mile every minute. So we can also think of the fact that 4 minutes per mile, if we take the reciprocal and then think of a rate as a distance per unit of time like we're used to, that would take the 4 and make it 1/4. That would put the miles at the top and the minutes at the bottom. So it takes us 1 minute to go a quarter of a mile, or 4 minutes to go a total of 1 mile. So if we go 4 minutes of pedaling, we will go 1 mile. Okay, so there's lots of ways to think about it, but if we turn it into more of a rate, that mile per minute sort of thing, then we that 1/4 is what we want. So in C it says, if we are riding a constant rate of 4 minutes per mile, how many miles will we go in 1 minute? That's that 1/4 of a mile. So could anybody tell me, first, don't just tell me the answer, but tell me, or you can tell me the answer, but tell me, how would we calculate, knowing what we know in part C1, how could we calculate how many miles or we would travel in 6 minutes? How could we figure out how many miles we would travel in 6 minutes? What do you think? Exactly. Now, another thing, you might recall a formula related to distance back in the day. Distance is rate times time. So if we have our rate, that is our standard rate, a unit of length per unit of time. We could also do that the distance is our rate times our time, which is exactly right, that you get 6/4, which is 3/2, or 1.5 miles. Now I'm okay you leaving it 3/2. That's okay with me. I'm totally okay with you doing it like that. Remember, for a pre-calc class, anytime we're doing algebra, preparing us for calculus, improper fractions are okay as long as they're reduced. So I don't like the 6/4 as much as I prefer these two as possible answers. Okay, so that would be my choice. And then we could keep going. If we traveled for a total of 9 minutes, our distance would be that rate. It has to be distance per unit of time. The time measurements have to match. So this was in miles per minute. This has to be minutes. So then we get to just multiply. And this time we get 9/4. Now 9/4 is acceptable as an answer. So if you just want to stop there, that's okay. But you can also do the fact that 4 goes into 9, 2.25, and you can make it that decimal. Now, if it's a strange repeating decimal, I do not want you to, stop that decimal unless they have asked you to round to the nearest. So I would prefer that fractional answer. So that leads us to D, and we've already talked about it a little bit. I kind of went a little quicker than that. Remember that distance equals rate times time. So what's interesting is, let's think about if we isolate the R. So our rate is going to be the change in distance over the change in time. Now in this particular case, remember they said that was a constant rate, so it was always that 1/4 of a mile per minute. But sometimes it might be a variable rate. So we might have to look, well, at what was the distance and time at this point? what is the distance at time in this point, and we might have to do some calculations. But because they gave us that this was a constant rate, we didn't have to really do anything. So remember, delta t is the change in time, and delta d is the change in distance. In this particular case, since this was a constant rate, that ratio is always going to be the same. It's always going to give us 1/4. Whether we calculate it at minute 1 or at minute 9, however we calculate it, from minute 1 to minute 9, from minute 2 to minute 7, all of those times we are going to always get 1/4. That happens, that constant rate is always going to happen in a linear equation. And that's what I want to show you in the next example. Okay. Do we have any questions about what we've seen in problem number 1? Okay. Now that leads us, I guess number 3 is actually going to give us a little more information. So let's the last time we did these questions, it had been, if we traveled for 1 minute, how far did we go? If we traveled for 6 minutes, I think it was, how far did we go? So we were given the minutes and we found the time. Here, we're going to go, what is the time if we know the distance, okay? So let me show you how you want to do that. You still want to think about the fact that distance equals rate times time. Do you remember how we found, remember that problem about Desiree running the marathon, and we found the length to the end in terms of her initial distance from the start. And they said in terms of. Well, we want this equation for time to be in terms of distance and rate. So if we took this equation and we solved for time in terms of distance and rate, what do we have to do to isolate that time so it's all by itself? What mathematics will it take for us to solve for time? What would we have to do to solve for the t? What do you think? Yes? Okay. Yes, we're going to do that very thing. But we're going to then have every single time to have to do that that division, right? What we can do ahead of time is if we isolate the t by itself, we get a new version of the formula that's going to give us what we want right off the bat. So my suggestion, although that is perfect, I'm going to show you what you can do instead is if we isolate the t, and if we know that t is always distance divided by rate, we can immediately then jump to 1/2 divided by 1/4. So that's the only benefit by doing it ahead of time. Your thinking is perfect. You can always do that. You can stick it into the formula and solve, but what are we doing? You are always isolating the t and dividing by the r. So if we just rewrite the formula for the thing we're trying to accomplish, it just will make it easier for us. So let me remind you a trick that I like to tell my pre-calc students, and I even remind my calculus students. If we want to divide fractions, we are multiplying actually by the reciprocal of your bottom fraction. But what you can do, I call it big C over little c. It's kind of a little trick. What will happen is when you do that multiplication of the reciprocal, you're flipping that bottom one. So the outer C, the big C, multiplies and gives you what's going to go on top. So the big C connects 1 and 4. 1 times 4 is 4. The little c connects 2 and 1, so 2 times 1 is 2. And so we get an answer of 2. Now, this context, that would take 2 minutes, okay? So that's a little trick that I will show you for fractions. Yes, you can rewrite it as a multiplication and then flip the other one, but that's just a nice way to do that. So for us to pedal a half a mile is going to take us 2 minutes. Okay. Now, part 2 says 1/10 of a mile. So remember, we have that new equation that it's distance divided by rate. Remember, for it to be a correct rate, we need to use 1/4 of a mile per minute. So that's what we're going to use as our rate. So in this particular context, the distance is 1/10. Our rate is 1/4. Do big C over little c. That puts 4 on top over 10. Reduce it as much as you can, and then stop. What are they both divisible by? What are they both divisible by? Yeah, by 2. So why not just divide them by 2? If we divide the top by 2 and the bottom by 2, we get 2 over 5, and that stands for minutes. So you'll go 1/10 of a mile in 2/5 of a minute, or 0.4 minutes. That's also acceptable. Those decimals that stop, I'm okay with you using the decimal equivalent. I just like the fractions. I want to get you used to dealing in fractions because fractions are very helpful in a calculus context. And hopefully one day you guys will take calculus. And then finally, the last one, our time is going to be our distance divided by our rate. Now, in this context, I think it's probably a good idea to just think of the division as a multiplication by the reciprocal. So if we multiply 3.2 times 4 over 1, that's really just multiplying 3.2 times 4. 3.2 times 4 is 12.8, and that would be 12.8 minutes. Okay, so that's a little bit about that. Do we have any questions there? Okay. Now, let's go ahead and take the information we saw in problem number 1, and let's create a graph of the situation. Okay. So it says you are riding a stationary bike. After your 2-minute warm-up, you begin pedaling at a constant rate of 4 minutes per mile for the next 5 miles. Okay. So let's think about what we want to, how we want to set up a graph. So here it says we will create a graph to represent the total amount of time spent riding in terms of the distance pedaled since beginning to pedal at a constant rate. Label the axes accordingly, including units, and complete each part. So they're going to they want to put distance here. They want to put time here. So this is going to be minutes, and this is going to be miles. Now, let's think for just a minute of some information that we know, okay? It says, use the coordinate plane and plot the point 0, 2 on the axes and describe what this point represents in the context of this situation. So we're going to put this point right here. I'm just going to count by ones. It'll just make everything good. If you don't label, then I'm going to assume you're counting by ones. If you decide to label it differently, then that's okay. So what does that mean? Well, at 0, 2, we know this is the start after 2 minutes of warm-up. So we have warmed up for 2 minutes. We haven't gone anywhere. We've just warmed up for 2 minutes. And that's kind of why that is what it is. Okay. Okay. Next, it says use the graph to plot 3 more points on your graph. So let's think about what we know. We know we're going in 4 minutes, we're going to hit a mile, right? So after 4 more minutes, so count from that spot, count up 4, 1, 2, 3, 4, and we have gone a mile, right? It takes us 4 minutes. That's our time. 4 minutes, we'll go 1 mile. So that would be the point 1, 6. What would be our next point that would be a good point to put on? What would be another good point to put on? Anybody have a good one for us? Yeah, let's do it again. Okay. Now it says we're going to do this for the next 5 miles. So let's count up 1, 2, 3, 4, and over again. And let's do it for 5 miles. So that's 1, that's 2, 1, 2, 3. I know they said only do 4. Let's just do the whole thing. 1, 2, 3, 4 over 1. 1, 2, 3, 4 over 1. We've gone 1, 2, 3, 4. 1, 2, 3, 4 over 1. So we've done 1, 6. We've done 2, 10. We've done 3, 14. We did a few more, but okay. It says draw a line through the points. What do the points that make up this line represent? I'm so glad that makes the line straight for me. Anybody give me an idea of what these points will be representing for us? Anybody give us an idea of what these points represent? Anybody tell us what these points? Yes.
The points represent how many minutes it's been when you hit each mile.
So one way you can think about it is, okay, let me write that down. So it is the minutes gone past for each mile. Now, let's also explain the fact of the way the point like 1, 6 tells us, okay? What's the point 1, 6 tell us? If we go the point 1, 6, or let's just call it xy, okay? The x, remember, is the distance we have gone, and the y is the time it took us. So we can go on this line, and at any point, if we just stop, not even the good points, but even those decimal values in between, and we will know that, oh, at a quarter of a minute, we have gone, or I'm sorry, at a quarter of a mile, we have gone 3 minutes. You know, we can actually relate those two things along any time during our journey. Okay, so that's the great thing about that line. It finds all those little decimal values along the way. So it says here, illustrate on your graph an increase of the distance from 1 to 4. So the distance, our distance is increasing from 1 to 4. So let's think about if I start at a distance of 1, that's right here. And then I'm going to a distance of 4. So that would be way up here. So that would be this change. So if we think about the fact that this is a change in our distance from 1 to 4, this would be our change in time. So let's think about what happens, okay? As our distance, our delta t changes from 1 to 4, so from here to here, or you can even look up here, okay? Our time is increasing, right? It takes us time to go 4 miles, or 3 miles, I'm sorry. And let's think about how many minutes it's going to take us. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it makes sense that as our distance changes by 3, our time should always change by 12, because that fractional change, since it's a constant rate of change, should always give us 1/4 when we're relating distance per unit of time. So it should always give us 1/4, no matter what 2 points along our graph we have chosen. That's what makes it linear. That's what makes it linear, okay? So we have a little sentence here to complete. It says, complete this sentence. When pedaling at a constant rate of 4 minutes per mile, any change of 1.5 miles result in a change of how many minutes? So we can make a little chart. Remember, it's a constant rate of change. So 4 minutes over 1 mile should be the same as, that did not look good. How about 4 minutes over 1 mile would be the same as how many minutes over 1.5 miles? So we can use that proportion to know that fraction should always reduce to 4 over 1. So if that fraction should always reduce to 4 over 1 if we're doing minutes over miles. So we need to find the number that would go there. Mathematically speaking, proportions are the greatest things to solve. You always are going to cross multiply. In this case, we are multiplying 4 times 1.5, which is 6. 1 times x is just x. So the answer is 6. That's really one thing that's really great about constant rate of change. Constant rate of change means that that thing will always proportionally give you 4 if you put minutes over miles, 1/4 if you put miles over minutes, okay? So that's something that's just super important. Now, let's go back and talk about the equation of this line for a minute before we finish this particular lesson. You might recall back in earlier even, I gave you that our y equals mx plus b was our equation of line. Remember, that's the first thing you saw today. So when we did that, let's think about this particular equation. Our starting place was 2 minutes because we've already gone 2 minutes, right? Okay. Our rate, because this equation, the change in y is time over the change in x, our slope is change in time over change in distance. So it's not 1/4, it's 4 over 1. Let's switch that around. It's always the change in the y value over the change in the x value, which in this case would be 4. So we actually have an equation to find any particular point along the line, as long as the x values that we are plugging in are distances. And so we get m equals 4x plus 2 would be the equation of the line. We would plug in a distance, we would find the time. We would plug in the distance and we would find the time, okay? So let's stop here. We're going to turn this in tomorrow when we finish this. So just hold on to this document. We'll finish it tomorrow. Um, at this time, open up your iMath and look at some of the things that are there. I think you have homework 2.2 is coming up. Maybe that's tomorrow by midnight. Check your dates. The best place to kind of see everything kind of all organized together is in your grade book. So take a look at your grade book. The grade book will help you. So there you go.